Dr. K.G.Valase from Mechanical Engineering Department of Walchand Institute of Technology, Solapur. In this session, we will be discussing about assignment problems wherein number of allocations at certain stage in the beginning we get are less than the required one. That is, if m is the order of table, we get number of allocations less than m. These things we have discussed in previous video. The same problem will be talking here and going to the final solution. At the end of this session, students are expected to understand how to solve assignment models, such problems, and at the same time the extended procedure for assignment problems wherein the number of allocations are less than the order of the table, as I have just mentioned. So coming back to this problem, we have discussed these things in detail in previous video. I will have a quick recap of what is done there. We have a basic problem wherein 5 towns are given A, B, C, D, E, and 5 depots are given small a, b, c, d, e like. And the table values here, what we call Cij values, they indicate the distance travelled. So distance between the towns and the depots is given in the cells, what we call symbolically as Cij. And this is how we have got a 5 by 5 table, and we solve this with a regular procedure. The very first step we have is look for the least element from a row and subtract that from all elements of that row. So if we just see here for a quick review of what we have done, second column has got the least elements in respective rows. So 130 is the least element of first row that we subtract from all elements that row. We get 160 minus 130, we get 30 here in the left bottom table. Then 130 minus 130 is 0. That is how we have to repeat the procedure for all rows and then all columns also. We have discussed these all things in detail in previous videos, and presuming you all know it, and I have explained also how to do it. Once you do it for rows, we have to repeat it for the columns also. Having done that, we are getting the table given in the bottom. Going ahead, in this particular table, we have to go for the allocations, and while we try for the allocations, we are getting only 3 allocations here. Again, a quick recap I will have for how do we go for the allocations. We basically look for a single zero in a row or a column. We start with the rows. First row, we have a single zero here, and this is the allocation in the row. Hence, all the rest zeros in the column we cross out so as to avoid any confusion for being assigned second time in that column. So to avoid that, we cancel additional zeros in the column. Second row, 2 zeros, do nothing. Third row, nothing. Fourth row doesn't have single zero. Fifth row has nothing. Now come to the columns. First column has a single zero here. We allocate that. This is allocation in the column. So 0 in the row, that we cross out. Then second row is already having an allocation. Third column, we allocate this particular cell. This is in the column. So additional 0 in the row, we cancel out. So this is how we get 3 allocations here, and but we need 5 allocations. That's the main thing. And again we draw the lines, and again the concept has been elaborated in previous videos. I will again say it briefly here. We draw minimum number of lines wherein all the zeros are covered, but a line while we are drawing should cover maximum zeros. Now here in a 5 by 5 table, any row or a column may have at the max 5 zeros. So this particular second column, if you see, has got 5 zeros. So that is the line we prefer first, and we draw that as a first line covering 5 zeros. Otherwise, we could have drawn 5 horizontal lines, but that is not recommended. Remember, I repeat, we could have drawn 5 horizontal lines for second column having 5 zeros. That is not recommended. One single vertical line in column 2 covers all 5 zeros. That is expected. A line should cover maximum zeros. Then secondly, in second row, if we have this particular line that covers 2 zeros remaining in that row, then fourth row also, if you see, 2 zeros remaining are covered by this line. So 3 allocations, we got 3 lines. That's how we have 3 allocations here. At this point of time, I expect you viewers to think of the remedy on such situations. What can be the way to resolve these kinds of problems? And of course, you think of some industrial cases also. Now coming back to this, we have drawn 3 lines here covering all the zeros for having 3 allocations, but we need 5, as the order of matrix is 5 by 5. Here we have the extended procedure to be discussed. We have to look to the smallest element from amongst uncovered elements. I repeat, smallest element from amongst the uncovered elements in the table, which in this case happens to be 15. So uncovered means this is like 30, 35, again 30 and 15, like this. The elements which are not covered by the lines, we call them as uncovered elements. So from amongst such elements, 15 is the least element. Now, what to do about these elements? There are 3 categories of elements in all. One is uncovered elements like 30 here in cell 1, 1. Second category is just covered elements like the element 0 in first row, second column, or element in second row, first column like 15. They are just covered by line. Third category of elements is element at cell 2, 2, where I am pointing my arrow here. Element at 2, 2 cell is having 2 lines intersecting at that cell. So thus we have got these 3 elements, and what to do about them is given here in the bottom. Subtract this least element 15 from uncovered elements like 30, 35. Secondly, add this 15 element at intersection points like at cell 2, 2. And thirdly, do nothing for the elements which are just covered by the line. So elements like this 0 in cell 1, 2, wherein the 0 element is just covered by the line, we do nothing, we leave that 0 as it is. So this is what is given in next slide here again, and you can check the values. 30 is uncovered, so from that 15 as least element we subtract, so 30 minus 15 we get 15 here. Then again row 1 column 2, element is 0 which is just covered by the line, do nothing there, so that 0 remains 0 as it is. And at intersection point cell 2, 2 we add 15, and that's how we get 15 here. Thus we get this complete table at the left bottom after performing these 3 types of operations on different types of elements. And this is how in this particular table, if we try to go for the allocations for single 0, as per the rule, first row has no single 0, second row also doesn't have, third row has a single 0 here, so we allocate it. This is the single 0 in the row, so additional zeros in the columns we cancel out. Then fourth row, no single 0, fifth row, no single 0. Coming to the columns, first column has a single 0, so we allocate this 0. This is allocation in the column, hence additional 0 in the row we cancel out. Second column already has an allocation. Third column we get a single 0 here. Additional 0 in that row we cross out. That is the basic requirement. Fourth column we have a single 0 there in the bottom. Additional 0 we cross out. And fifth column now left out single 0, we get this allocation. This is how we get 5 allocations to this particular table of 5 by 5, and while we transfer these cell allocations into original table, we get these red marked values in this particular left bottom table, and adding all those we get final solution to be 570 kilometers. That is the final solution of this particular case of assignment problem, wherein initially we have number of allocations 3, like less than 5, which is the order of matrix, and with the extended procedure we got it 5 allocations. We have these 3 references of the books, Taha, S.D. Sharma and Hira Gupta. Thank you.